Okay, folks, welcome back, everyone. How's homework 2 going? Homework 2? So-so? I've got a couple thumbs up. Yes, I just want to respond to something that there was a couple of people who who sent in anonymous feedback saying, "Sir, I handed in my homework late. Can I please get marks?" I'm sorry. I wrote the thing down, and if I change now, you'll all hand it in on Friday. So my apologies. Please make sure that you hand in the homework 5 minutes after the start of tutorial. Okay? If you're having difficulty getting to tutorial because maybe you take transit or you have a class on the other side of campus, then I really highly recommend emailing the solutions to your TA. Okay? So the TA's emails are on the course webpage, and if you're not certain that you'll be able to hand it in on time, just take your phone and try and get as steady of a shot as you can of the homework and email that in. Okay, so I just wanted to say, please try and get them in tutorial within the first 5 minutes. Okay, so we're going to pick up with limits and continuity. So the plan is to do 1 hour of limits and continuity, and then to kind of move into derivatives and stuff. So the next hour is going to feel pretty proofy. There's going to be a lot of proofs. And then the hour after that will sort of feel like good old-fashioned calculus. Okay, so let's get into limits. Okay, so we defined in complete generality what we meant by the limit x goes to y of f of x is z. Okay, so try and write down the definition of this limit using epsilons and deltas. Okay, so try and complete this sentence. This limit is equal to z if for all epsilon greater than 0, what happens? Okay, so try and take a moment and complete that sentence. Okay, hi, welcome. Okay, so what happens here? So we say that this limit goes to z if for all epsilon there is delta greater than 0 such that if this distance is less than delta, then this distance is less than epsilon. Okay, so the idea is that if x is close to y, then f of x should be close to z. Okay? If x is close to y, then f of x should be close to z. Okay, so that's our formal definition of a limit. And we're going to now introduce sort of the key concept surrounding limits, which is the notion of continuity. Okay, if we've got a function that goes from n-dimensional Euclidean space to k-dimensional Euclidean space, we say this function is continuous Okay, this function is continuous at x equals y if we have the following thing. Okay, if the limit as the function approaches y is equal to the actual value of the function at y. Okay, so the idea is that the limit agrees with the function. Okay. So that's a, yeah, yes, sure. Yes, that's continuous at the point y, x equals y. Yeah, right, so that's continuity at one point. Okay, so let's enlarge that to a bigger definition. Oops. Okay, we say that something is continuous on a domain D if it is continuous at each point in a domain. Okay, we'll often say that something is just a function is continuous if it's continuous on its domain. Okay, so these are sort of three different ways in which we use the word continuous. This sort of at a point, on a set, and then just in general. Okay, so there's sort of three different levels of the way we use that word. Okay, very good. So I want to say a couple key properties about continuity. Okay, if we've got two functions that are continuous at a particular point, okay, so if we've got two functions that are continuous at a point, then we have the following that are also continuous at that point. So the first is where we take our function and we scale it. Okay, so we stretch our function by some constant. Okay, the next is where we add them together. Okay, so we can add continuous functions together. And the last is where we multiply two continuous functions together. Okay, so let's try and get into the proofs of some of these facts. Okay, so these are going to be examples of delta epsilon arguments. Okay, so where we really use this definition quite carefully. Actually, you know what? I'm probably going to need the whole board. Okay, so let's prove fact 1. Okay, so our first observation is that if k is 0, then this is very straightforward, right? If k is 0, then we've just got the 0 function. That should be continuous. So observation. Okay, and we should really hope that the constantly 0 function is continuous. Okay, so suppose k does not equal to 0. Okay, and now we have to do a little bit of a clever argument. So this argument has 2 parts. The first is our hypothesis. We know that this guy is continuous. So by hypothesis, okay, by hypothesis we have this limit, which means that for all, and I'm gonna give this guy a special name. I'm going to say for all epsilon greater than 1, or sorry, for all epsilon 1 greater than 0, there is delta 1 so that the following thing happens. Okay, so this statement I've just written down is our hypothesis. Oh, yeah, so I see that there's like a bunch of people coming in. I just want to say that the next half hour for you guys is going to be quite proofy. Okay, there's going to be a lot of proofs. After that, we're going to get back to good old-fashioned calculus. Yes, sure. Yes, it should be. I got them confused because everyone was showing up. Welcome, everyone. Yes, very good. Okay, so if these guys are delta 1 close, then these guys are epsilon 1 close. Okay, so now comes the hard part of the argument. Okay. Okay, so our goal is to get that k in there somehow. Okay, so we need something involving k. So what we need to do is we need to talk about the delta epsilon argument, or where there's a k involved. So we're going to say, given epsilon bigger than 0, pick okay, so now this is a really, at least at the level of quantifiers, this is a very complicated statement. So what are we saying here? Given a positive epsilon, we're going to pick delta to be the value delta 1 that this theorem gives us. Okay, so these sort of delta epsilon arguments, you can kind of think of them like a function in a computer program, right? You input delta, the delta epsilon argument outputs a delta. Okay, so you give it epsilon 1, it outputs delta 1. Okay, so we're going to ask our program for the delta 1 that comes from this epsilon 1. Okay, so we put that into our hypothesis. We ask it for epsilon 1, it gives us delta 1, and we'll use that. Okay, so let's see what that gives us. So that gives us x minus y is less than delta, implies that f of x minus f of y is less than epsilon 1. Okay, so if we're less than delta 1, then this is less than epsilon 1. Okay, and we've got a value for that, and it has this k in the denominator here. So what we're going to do is we're going to take this statement and we're going to multiply through by k. Okay, we multiply both sides by k, and we get this thing's less than epsilon. Yeah, sure. Right. Good question. Yeah, why is there this absolute value here? Okay. This ensures that we can multiply by k on both sides, and the inequality stays in the same direction. If k was negative, like negative 10, then this inequality sign would flip, and the argument would blow up. Okay, so we want that we can multiply by k and keep order. Okay. Any other questions about that argument? Right, so I guess the argument has two parts. It is the part where we write down this hypothesis, and then this part where we use that hypothesis to give us the delta we need. Okay, so we plug in the epsilon we're given into this hypothesis, it gives us a delta, and we run through with that delta. Okay, so far so good. So I want to prove statement 2 as well to give you a feel for how these arguments go. Okay, so let's prove this fact about adding together limits and see what we get there. Okay, so by hypothesis, okay. I erased the statement. By hypothesis, remember, by hypothesis, okay, so we've got these two statements, right, that this guy limits to f of y, this guy limits to g of y. Okay, so both of these statements give us epsilon delta routines or epsilon delta functions. Okay, so okay, now I'm going to call these guys the epsilon and delta depending on which function they come from. So epsilon f will be our guy for f, delta f will be for f. Okay, so there's the epsilon delta statement for f. Oh, yep, thank you. Very good. Thank you, you're doing good work. Right. Yes, okay. This is the part of the course where my dyslexia really shows. Okay, so we've got epsilon g, there is delta g. Okay, very good. So there's our epsilon delta statement for g. And now we're going to combine these two together. Okay, so we want to control this sum. So we want we need this statement. Okay, so in order to control this, right, this is the guy that we eventually want to bound for our epsilon delta argument. We observe the following. So this is the following thing. So if we've got an absolute value here, we can split it up into two parts. Okay, and now we've got control over both of these. Okay, so we want to control this final thing, right? This is what our epsilon delta argument wants. So we can control both of these guys. This guy by epsilon f, and this guy by epsilon g. Okay, so in order to control the final statement for our limit, we use epsilon f for this part and epsilon g for this part. Okay, so now we have to make a setup that'll give us these properties. Okay, so let's write down sort of the complete or final epsilon delta argument for this limit. So okay, so given a positive epsilon, we pick epsilon f to be less than epsilon over 2. We pick epsilon g to be less than epsilon over 2. Okay, when we feed epsilon f into these statements, we get delta f. When we feed epsilon g into this statement, we get delta g. So we've got two deltas in question. We've got delta f and delta g. So we're going to pick a value less than those values. Okay, we obtain okay, if we are less than delta, then we're less than delta f and less than delta g. Okay, so from our hypothesis, if we're less than delta f, then this is less than epsilon f. Good. Right? And now following this reasoning here, oh yeah, sorry, there's a question? Yeah?
Oh,
Perfect. Yes. Yes, very good. There's supposed to be g's involved, yeah? Good. Yes. Yes. I really like it when people spot typos because that helps everyone else in the class, and it means at least one person's paying attention. Very good. So we're here. We've controlled these guys. So this gives us, following the reasoning up here, okay, using the reasoning up here, we got that this is less than this. Okay, now we picked epsilon f to be less than epsilon over 2, epsilon g to be less than epsilon over 2. So our final thing is less than epsilon. Okay, very good. So it's a long argument. What are the steps? So we write down our hypothesis. We write down what that hypothesis is telling us in terms of epsilons and deltas. We write down the thing we want to control, right? We phrase it in terms of epsilon g, or sorry, epsilon f and epsilon g. Then we pick our final epsilon and delta to exploit these hypotheses, and then we plug them in. Okay, so very sophisticated argument. Lots of moving parts there. Are there any questions about the technique or the proof? A perfectly reasonable question is, what the hell? That's completely all right. Yes, sure.
How do you select? How do you know that the criteria is epsilon?
Oh, right. Why on earth do we say epsilon over 2? Why do we say minimum? All this stuff. Right. Key question. Right? Why do we, these are the three sort of choices that we make in our argument. Why do we make these choices? So when we get to this stage, right, we've got two terms, we're adding them together, and in the end we want something less than epsilon, right? So in our epsilon delta arguments, we always want the last line to be less than epsilon. Yeah? So now we've got two terms, we can control them both, and we want them to add up to something less than epsilon. So I just split epsilon into two parts. Right? So I could say, you know, epsilon over 2 plus epsilon over 2 is epsilon. So I split it equally into two parts. That's why I make the choice epsilon over 2 here. Okay? I could also take, you know, epsilon over 10 and then 9/10 epsilon if I wanted to be very strange. So I don't want to be strange, I just split it equally. Yeah? Okay, yeah, another question? Yes, yeah, it works if you set it equal to the minimum. Yeah. The reason I pick the minimum of these two numbers is that I want both of them to happen. Right? I want to be able to go from if I have this one delta, then I want to know that I'm smaller than both of these two numbers. I want to know that I'm less than delta f, and I want to know that I'm less than delta g. So I pick the minimum of the two. Yeah? Then I'm smaller than both. Okay, yeah, sure.
But I'm kind of confused about the inequality. It's like, if you're choosing the earlier one and one is that means the other one will be bigger. But there's a chance that it will be bigger than
So you're saying what happens if I put equals here?
No, like I'm just saying there's a chance of one of them could be bigger than delta.
Yeah, it's fine if one of them is bigger. If it turns out that this is 1 and this is 1,000, that's okay. Just as long as I'm less than the smaller one. I want to say, okay, I'm less than 1. So both of these things happen. I'm less than 1 and I'm less than 1,000. Okay? It's okay if one of them is much bigger. Just as long as I know that it can make this move where I wind up being smaller than both. Does that help at all, or does that make things worse?
What about like delta G were 1,000 and then delta were 999?
Yeah, sure. So let's say delta F is 999. Delta G is 1,000. Okay, I need to pick a number.
No, I mean like delta itself is 999.
Oh. Okay. Like this?
Where delta F would be 1 or something.
Okay. So that's bad. Yes. Good. Okay. Key question. Yeah. Very important. Right. So this situation is this is exactly the situation I want to avoid. Okay. I want to avoid picking a delta that's bigger than one of these two, because then, let's say we got that circuit. Let's say we're in that situation. Then delta would imply delta G, right? But it wouldn't imply delta F. And that would be bad because I need delta F. So we need to be able to get this implication to delta F here, right? And that's the reason why we always pick a minimum. We want to make sure that we don't have delta in between delta F and delta G. It needs to be smaller than both. Any other questions or thoughts there? Right, so with these kinds of things, it requires a fair bit of practice to get used to this. This isn't the kind of thing you can do the first time, okay? A lot of people in my Math A31 class asked, how do you pick epsilon? Or how do you pick delta? And I said, well, I write the lecture notes at home. I write it down in advance, and then I come and I tell you what to pick. So it's practice with these kinds of techniques. Okay. Okay. Good. Oh, geez. Okay. So I want to do another example of this technique that we were calling the circle and box argument last lecture. Okay, so you won't find this in the textbook. I just made up this name myself, but it's a very important technique. So I want you to absorb it because it is helpful for some of the homework questions. So, okay, so I think on the homework there's a question involving a maximum function. Here we're going to do an argument involving the minimum function. Okay, so to show this limit, what do we need? Okay, so we need one of these epsilon delta pairings again. So we need that if the distance from 0 is less than delta, then and this is less than epsilon. Okay, so we've got our inputs are less than delta, and our outputs are less than epsilon. Okay, very good. So we have to pick delta. We have to pick delta to make this work. So I want to say how we can control these absolute values just working from this hypothesis. So our question is, right? How do we control these values given that this is less than delta? So the answer to this is this circle and box argument. Okay. So what's the circle? The circle is the set of points that are less than delta. Okay, so in the xy plane, this point here will be delta 0. So we've got a circle of radius delta. Okay, and now if we're a point contained somewhere in that circle, right? Then what do we know about the x and y coordinates? Well, the biggest they can possibly be is delta. So we're going to say the biggest our y coordinate could possibly be is positive delta. and the smallest it could possibly be is negative delta, right? This point, it can wander all the way up to positive delta, or it can wander all the way down to negative delta. Okay, going the other way, the most negative x can get is negative delta. And the biggest it can possibly get is delta. Okay, so we know based on this picture that the blue lines, oh yeah, sure, yep.
Shouldn't the bottom one be epsilon, not delta?
No. Good question. Yes, that would be what would happen if we were in one variable. Yes. In one variable, the horizontal stuff would be deltas and the vertical stuff would be epsilons. However, this function that we're considering, right, our function goes from R2 to R. So this whole picture is happening in the domain of our function, right? Usually our functions go from R to R in one variable calculus. But here, this whole picture is happening in the domain. Okay? Maybe we'll chat about it during the break. Yeah, we'll chat about it during the break. Okay, so coming back to this picture, we know that y is between delta and negative delta, and we know x is less than delta. Okay, so these two things cannot be close to delta at the same time, right? Our point could wander up to, say, here, and it's in this circle, and it can never get into the corners of the box, but we don't need the corners of the box. We just need to know both of these quantities are controlled. Okay? Very good. Okay. Any questions about this setup so far? Okay, so let's use this setup to control this function. Okay, so we want okay, so we want these two quantities to be less than epsilon, right? So if the minimum is less than epsilon, then one of these guys has to be less than epsilon. Okay, so what we'll do is we'll pick delta to make sure that that happens. Okay.
Or active value y?
Yes, thank you. Yep, good. Okay, sweet. So okay, so we're going to pick it less than epsilon over 2. We're going to pick it less than epsilon over 4. Okay. if this is less than delta, right, then this step here, this implication, is our circle and box argument, right? If you're less than delta, then both of your components are less than delta. Good. So we get both of these. Yes.
I was just wondering for the delta, right? So you chose delta less than epsilon, so we would delta less than epsilon 4.
Yeah.
Usually don't you do like delta 1 and delta 2 since those are two different values?
Right, sure. Yeah, so I sort of say, pick it to do this and to do this, right? I guess we could replace this with we know which one's the minimum. Right, so we could just pick it less than epsilon over 4. That would give us this statement, it would give us this statement, and then would be good to go. Okay, yeah, question? Yes, there's also a way to prove this using cases. This kind of like, this sort of all the x business happens in this column, right? And all the y business happens in the other column, but you could do them as two separate arguments. Yeah? Over here? Yeah? Hmm?
You can actually choose either delta, right? Because we just have to prove 4. So if you pick epsilon over 2, then prove that epsilon 5.
Let's see, if we pick epsilon over 2, I'm just slightly worried about what will happen if y is big. So if we pick epsilon over 2, then I'm worried about this multiplication by 4 here.
So you said that you want to show that either 2x is less than epsilon or...
Yes. Okay, yes. You could just force this one. Yes, you could just make that one always the minimum. Yeah, okay. Yeah, that would work too. Okay, any other questions or thoughts about this argument? Okay, so it's 10:04 now. I'd like to take a break for questions till 10:10. So we've got 5 minutes. So if you've got questions, please come up and ask. Yeah. So there's a couple more words that we need to talk about limits and continuity and stuff. So I want to quickly introduce a little bit more vocabulary, and then we'll get back to derivatives and such. Okay, so I want to talk a little bit about topology and continuity. And if you're a math person, topology is where it's at. Topology is amazing. I remember, just reading all these books about topology as an undergrad and being like, this is the best math. So we'll do a little brief intro to topology in order to say the correct definition of continuity. Okay, so the first thing that we need is the definition of open. Okay, the open disk okay. All right, so the open disk of radius r at x is the following guy. Okay, so it's going to be the set of all points that are distance at most r from x. Okay, so this is just a disk centered at x. So if we've got the point x here, then this guy is drx. And it's important to note that the boundary is not included. Okay, this set of points where its distance is equal to r is not included in the set. Okay, so that's the open disk. Very good. So okay, what is this guy just in the real numbers? In the real numbers, we're going to have some value c. We're allowed to go down to c minus r and up to c plus r. Okay, so this will be the range of points we care about. So it is the following guy. Okay, so in one dimension, these are intervals, and then in the plane and stuff, they're disks and they're balls in space. Okay, so the purpose of these is to let us phrase epsilon delta arguments in a bit of a nicer way. So the purpose right? So instead of all these inequalities and stuff, we can phrase these things in terms of open disks. So if for all epsilon there is delta such that Now we've stated things in terms of disks. Okay, so if you're in the disk of radius delta about y, then F is in a disk of radius epsilon about z. Okay? So this phrase is our condition of being a limit in a sort of a nicer way. Okay? And I want to say an even nicer rephrasing of things. Okay, so we've defined an open disk. So we're going to say that a subset is open okay, if for any point in that set there is an epsilon such that d epsilon u is contained in our set. Okay, so that the disk of radius epsilon is contained in our set. So intuitively this means that any point in our set can be surrounded by some disk. Okay, so that's the definition of open. Let's just have a look at a couple examples of open things. Okay, so the sort of the straightforward example, or the first example, is that Rn is open. Right? Any point in Rn is contained in some disk. So for any we have that there's a ball of radius 1 around that point. So all of Rn is open. We could pick any radius we want, and I pick 1 just, it's a really nice number, I guess. Okay, so that one's open. Let's see a non-example. Okay, so the point just containing, or the set just containing 0 is not open, right? Oops. Right, we can't pick any value epsilon that will make this work. Right, there's only one point in here, and all of these disks have infinitely much stuff in them. Okay, so that one's not going to be open. Okay, but a lot of oh yeah, sure. Yep.
It's closed.
No, we can't. Open's a very tricky word. And weirdly enough, its antonym is not open. So, yeah, I'm not going to get into closed right now, but that's a tricky thing. So, the set could fail to be open. Okay, so this is just weird. Okay, we'll talk about more topology later, but today we're just going to talk about this word open, because there's a question about it on the suggested problems. Okay. Okay, so let's check that this fellow is open. And we'll see what we have to do to show that a set's open. So with this, it's helpful to draw a sketch of the thing. Okay, so there's our sketch of it. This is the line y equals -2. This is the line y equals 2. And now we want to argue that any point in this is surrounded by a disk. Okay, so any point in here is surrounded by some disk. Okay, so it's intuitively obvious. Let's try and write down an argument that proves this. Okay, so what radius should I pick for the disk? I need to surround this point here with a disk. What radius should I pick? It's okay to be wrong. Guesses are fine. Yeah, something about the edges, right? So what's interesting is that my disks will have to change radius as I move around. If I'm here, it'll have to be small. It could be small here, but it could also be very big here. Right? So as my point moves, the set of allowable radii is controlled by the position of the edge, or position relative to the edge. So can we write down a formula that will give us something? Yeah.
2 minus y.
Yeah, that's a pretty good idea. 2 minus y. Yeah. So let's say pick epsilon to be 2 minus absolute value of y. I think that's what we want here, because as we get closer to the edge, the allowed radius goes down and down. So we have that 2 is less than y. Okay, so that means that our epsilon's positive, and we get this point's controlled. Okay, this point lives inside U. So thus, this U is open. Okay, and as our point moves closer and closer to the boundary, it'll get a smaller and smaller disk. Okay, very good. So that's an example of an open set. There's some of these kinds of, prove such and such set is open on the suggested exercises. And I just want to say why we've introduced this whole terminology. So the very nice and very general way to say continuous is as follows. Okay, so I have to say what I mean by F inverse here. So this is going to be all of the x like this. Okay. So we say that a function is continuous if this is open for any open set U. Okay, so our definition in terms of epsilons and deltas can be rephrased in this way. So I guess the big exercise is to check that this rephrasing is equivalent to epsilon delta continuity. Okay, so this is a very helpful term, continuous. It's helpful to phrase it in terms of open sets, and we'll need open sets later, but for the rest of the lecture I want to talk a little bit about derivatives and other simple things. Okay. Okay, so now we'll head back to the land of normal calculus and such. Okay, so for functions of two variables, we have two derivatives at the same time. Okay, so the partial derivative with respect to x, we pronounce this. Oops. Okay, so df dx is the following limit. Okay, and we call this df dy. Okay, so what are these guys measuring? Okay, so what's the physical significance of these derivatives? Okay, so they represent the rate of change in two different directions. Okay, so recall that this is our x-axis here. Okay, and what df dx measures is the rate of change in the x direction of our function. Okay, so okay. Oh, I guess one thing I should say, this symbol here, this D, is supposed to be a fancy kind of calligraphic letter D. Okay? One time I was teaching a course on this, and we got, 3-4 weeks into partial derivatives, and someone said, why do you always multiply f by 2? And I was like, oh no. Okay, so this is a D. This is the letter D. Okay, it's like this. And yes, it does look like my 2, which looks like this. That's okay. So, why do you always multiply f by 2? Okay, very good. So that's what df dx measures, and then dy dx measures the same thing in the other direction. Okay, so df measures the rate of change in y direction. Okay, so let's find some of these partial derivatives, just working with the definition. Okay, so just using the definition, Let's see what we can do. Okay, so we'll substitute in. Okay, and these x's, right, these x's always cancel off. But I write them there just to remind you that this is a slope. So we'll cancel them down to h. Okay, very good. Okay, now the xy squareds cancel. And we get y squared. Okay, let's do what happens in y now. Very good. Okay, and there's a little bit more algebra to work through here. We have a little bit of cancellation that can happen. Okay, so we've got this xy squared. That will cancel this guy. We can cancel an h. And we're left looking at okay, very good. So we've calculated these two partials. Okay, so what are these guys measuring? These guys are measuring the rates of change of this function in two different directions, in the x direction and in the y direction. Okay, so we've got these functions. Each variable gives us a partial derivative. Okay, so we don't need to just do things for two variables, we can do them for n variables now. Oh yes, during the break someone asked about this notation. I just write it because it's clear to me. So this means that we've got n inputs. Right? Your function has n inputs and 1 output. Okay, so you take n-dimensional vectors and you output real numbers. Okay? So for a function like this, okay, we get n distinct partial derivatives. Okay, for each variable we get a partial derivative. Okay, and just a reminder, these guys EI, these are the basis vectors. EI has a 1 in the ith position. Okay, so let's have a look at that. Okay, so if we're looking at the z coordinate, we're going to add a small vector in the direction of z. So this will be like this. Okay, so we add stuff to the third coordinate. Okay, so whatever coordinate we're taking the derivative of, we put the h in that slot. Okay, we put it in that coordinate. Okay. Okay, now these guys cancel. And our final limit will be xy. Okay, very good. So this is kind of the simplest generalization of a one-dimensional derivative that we have. When we look at these examples, we sort of see a pattern emerging. So for this example, we're taking the derivative in x, and we see that we just take the derivative in x, and we wind up getting y squared. Here, we take the derivative in y, and we get 2y, but x stays the same. X stays fixed. Here, we've got 3 variables. We take the derivative in z, but x and y stay fixed. Okay, so the sort of the the idea or the shortcut of partial derivatives is the following. Okay, so to calculate the derivative of f in the variable xi, okay, assume that all variables other than xi are fixed constants, and then differentiate in xi. Okay, so this agrees with our philosophy of what df dxi represents the rate of change in the variable xi and only the variable xi. So all the other ones we assume are constant, and then we look for the rate of change there. So let's see an example of this. Okay, so for something like this, if we want to find the derivative of x times e to the y, then we're going to assume that y is constant. Okay. So we take the derivative here. The derivative of e to the y squared will give us x to xy e to the y squared. So this happens because we apply the chain rule. We've got e to the stuff, so we get that stuff times the derivative. Okay, so this is sort of the sort of shortcut way of finding these partial derivatives. Are there any questions or thoughts? Okay, so we're going to pick this material up at the beginning of next week. If you're taking PDF notes, please send them in. It's very, very, very helpful to have copies of student notes, so please send them in. And if you've got any questions about the homework, etc., I'll be here for about 5 minutes, and then office hours. Oops.